Today, I'm going to present a proof of the sum of the squares formula using mathematical induction. Proof by mathematical induction is a basic tool in pure and applied mathematics. This presentation illustrates the use of such technique in proving some statements involving natural numbers. This may arise in areas in number theory, calculus, combinatorics, statistics, among others. To prove a statement involving natural numbers by induction, we have to establish first the base step. Here, we have to prove that the statement is true for some natural number, say n equal to 1. Next, we have the inductive step. We assume that the statement is true for some arbitrary positive integer n equal to k, and we're going to prove that the statement is true for the next positive integer n equal to k plus 1. If we can prove that these two statements are correct, the basis step and the inductive step, then we can conclude that the statement is indeed true for all integers n greater than or equal to 1. I will now present a proof of the sum of the squares formula using mathematical induction. First, let us denote a function s sub n to be the sum of the squares of all positive integers up to including n. So s sub n is 1 squared plus 2 squared plus 3 squared all the way up to n squared. So for n equal to 2, s sub 2 is 1 squared plus 2 squared, so 1 plus 4 equals 5. And then for s sub 3, we have 1 squared plus 2 squared plus 3 squared, so 1 plus 4 plus 9 equals 14. And then for s sub 4, you have 1 plus 4 plus 9 plus 16, therefore we have s sub 4 equal to 30. Now for small values of n, it's easy to compute for the sum of the squares by just applying the definition. However, for large n, we will going to derive a formula that will easily be used to compute for s sub n. So we're going to prove the following statement. The sum of the squares beginning from 1 up to n, denoted by the symbol summation of I squared, is n times n plus 1 times 2n plus 1 over 6 for all positive integers n. Now to prove that by induction, since we want to prove that the statement is true for all positive integers n, so we first establish the base case. That is, we will prove that the formula is true for n equal to 1. So if we replace n equal to 1 in the property, s sub 1 equal to 1 squared, so we get 1 times 1 plus 1 times 2 times 1 plus 1, so s sub 1 equal to 1, and therefore the statement is true when n equal to 1. Now next we have the inductive step. We assume that the formula is true for an arbitrary integer n equal to k. That is, we're going to assume the following statement. S sub k equal to k times k plus 1 times 2k plus 1 over 6. We call this as the hypothesis of induction. Now this is just the property that we assume to hold for n equal to k. Now using this hypothesis of induction, we're going to show that the formula is also true for the next integer k plus 1. That means we will want to prove that s sub k plus 1 equals to k plus 1 times k plus 1 plus 1 times 2k plus 1 plus 2 all over 6, which means that we will going to prove that each statement given by this is indeed true. Now to prove this, first take note that s of k plus 1 is just the sum of all the squares beginning from 1 to k squared and then the additional term k plus 1 squared. Therefore, s of k plus 1 is just s of k plus k plus 1 squared. But then by hypothesis induction, we already assume that s of k is k times k plus 1 times 2k plus 1 over 6. So therefore, we have that equation, and then combining fractions, taking the least common denominator, s of k plus 1 equals to k times k plus 1 times 2k plus 1 over 6 plus 6 times k plus 1 squared over 6. So, combining fractions, simplifying, factoring k plus 1 at the top, we have s of k plus 1 is k plus 1 times k times 2k plus 1 plus 6 times k plus 1 all over 6. Simplifying further, by distributing, we have a k plus 1 multiplied by 2k squared plus k plus 6k plus 6 over 6. Adding like terms, and then factoring this 2k squared plus 7k plus 6, we have k plus 2 times 2k plus 3. Now we can easily check this by foiling it, and therefore we have s of k plus 1 equals to k plus 1 times k plus 2 times 2k plus 3 over 6. And this is precisely the formula that we want to prove. Therefore, the formula is true for all positive integers by the principle of mathematical induction.